Good afternoon, everyone. So let's get started here. So my name is John Studeris. I am one of the members of the Openstack user committee. I'm also a cloud architect. Today we're going to be talking about edge computing, the position of open source in edge computing, and the changes that are happening in the edge, and a little bit about some new wireless spectrum that's becoming available in the States and how that's impacting edge computing, and a little bit about some new data centers that are being deployed across the US at cell phone towers, so co-located. So with that, let's jump into things. Okay, so first off, over-encompassing theme about this presentation is the edge is open. I want to focus in on the fact that the edge is open source. You're going to see a lot of different types of open source. You're going to see open source software as well as open source technologies. I want to showcase how the edge is open to all. What used to be a very closed garden and walled off garden where the regular user couldn't have access to the edge computing, that's definitely changing. The edge is open for business. If you're interested in using edge computing and getting your compute out for your business out to the edge, it's definitely becoming possible and opportunity to make money. And the edge is open for improvement. So the infrastructure is being rolled out, but there's definitely some areas of improvement, and hopefully you can walk away with some ideas where you can help out. This is a slide I stole from the last Openstack Summit. Just a quick overview of what edge computing is about and the whole idea behind moving from regional data centers towards smaller data centers that are closer to the end user. So what happens is as you move your applications down from those regional data centers, local data centers, to these edge data centers, the latency gets reduced, and there's certain applications in the world that benefit from that reduced latency. So bandwidth goes up, latency goes down, so great for these new killer applications that are coming to market. Historically, those edge locations haven't been available. We're going to talk about how those are now available. Okay, so edge computing, most people think different ideas of what is the edge. So I got a couple examples here of what people think about what an edge location might be. Lower left-hand corner is people's cell phones. You know, the mobile device in your hand. Is that the edge? Could that be defined as an edge location? We got new versions of Kubernetes that run within a mobile device. And some people consider mobile devices edge locations. We have in the upper left, mobile cell phone towers that are in the back of trucks and roll out, and those set up microcells. Could those be considered an edge? And then on the right here, we've got some smaller containerized locations that are co-located at cell phone towers that historically have been closed and only available to the incumbent telcos. So you as an end user wouldn't be able to deploy your applications at those locations. I would tend to say that the mobile devices do not have enough CPU and storage to really be considered the edge, an edge location where you can get the processing done that needed. The truck there doesn't have any compute on it. All it is just a cell phone tower. So yep, it'll bring bandwidth in, but it doesn't give you any compute locations. So what I'm going to be focusing on is on the right-hand side, these micro data centers that are being turned on and opened up and made available to the general public for use. So what's the sort of the killer application here for edge computing? So in this example here, we've got self-driving cars, autonomous cars, and edge computing is really starting to become a requirement for them. And the reason is that you can't put enough power inside the car. You can't put enough computers, image processing, storage, so somehow you need to get back from that car to a local tower, someplace that's close by that the multiple cars driving down the freeway can talk back to a central location, do the processing that needs, and the responses get sent back to the car in ultra low latency, so the car can react to any change in condition, and that central computing, that edge location, can get the messages back. So sending the message all the way back to a regional data center the processing happening, and then the latency of sending the message back to the car is going to take too long, and we're going to have the cars, unfortunately, driving over people. This is a slide from a summit out in Las Vegas. Last year, IFX, where they talked about some of these edge computing issues, and a good slide here that says, the edge is where the digital and physical worlds intersect. It's the location where there is enough data processing and storage and ultra-low latency for that work to be done. Okay, so let's talk a little bit more about the open source technologies out there. One of the first ones out there that we're seeing at these edge locations that's really making it feasible is ARM. So ARM, for those of you who aren't familiar, is started in the cell phone world, is a low power, open source. So if you want to go and build your own ARM chips, you can. It's not binary compatible with x86. So you do need to go and recompile your software to run on ARM or interpret it. But the idea being that it's a cheaper chipset, you can go out and roll it out. Since it is lower power, it's ideal for data centers, for these edge data centers. Since it's lower power, it also generates less heat, which requires less cooling. You can do higher density, and in edge locations, co-located cell phone towers, you don't have as much space, you don't have the power to do all that cooling. So you're seeing a lot of ARM systems being rolled out. Sort of working our way up the stack, the next thing we have is a couple of other open standards. Once again, these are another open foundations, much like the Openstack Foundation exists. We've got the Open 19 Foundation. 19 is referring to the 19-inch racks that we have. So what Open 19 is doing is they are open sourcing all the standards and blueprints to build common chassis and enclosures to roll out and deploy physical infrastructure, as well as common cabling. And the idea being that you could take the edge locations, run something like Open 19, have common standards, and make it easy for an independent person that wants to come in and install equipment in there, can just simply roll it in, put it into the cage, put it into the rack, all following a common standard for power and cabling, and it just plugs right in. And then the Open Compute project is the same sort of idea, but around network devices, motherboards, and opening up the market to common standards for that type of infrastructure. So we've got the hardware standardized, and we've got it being provided in an open source format, which drives down the cost and makes it available to everyone. So Vapor.io, they're one of the companies that's going out and building these enclosures and rolling them out at cell phone towers. So they're another part of the puzzle there, making these enclosures available and the uplink back to the internet. Now, interesting thing, a lot of people consider that you're going to need to have a lot of bandwidth at one of these edge locations going back, but not necessarily. The goal is to do the processing and the storage of the data at the edge location. So you got the IoT device, you've got your mobile cell phone device communicating back to the cell phone tower to some storage here, and all the work is being done here as opposed to backhauling it back and needing a lot of bandwidth, either fiber or some type of microwave relay or something back to another data center. So oftentimes you can get away with doing much less backhaul network connectivity. Okay, so in the States here, most other countries as well, wireless spectrum is auctioned off by the government to telcos, and we end up with a somewhat closed environment and walled garden. So if you want to use spectrum, if you want to use 4G, 5G, you have to get it from one of the telcos. You have to buy the spectrum there. So in the United States, we've got some new spectrum becoming available. This is actually recycled spectrum. It's called CBRS, Citizen Broadband Radio Service. It's an old military band the Navy used along the coasts that they're no longer using. That is becoming available. Right now, the US government is providing provisional access to it, with the goal is at the end of the third quarter of this year that the spectrum is going to be available across the states. People ask me about other countries, is it going to come to other countries? And from what I hear is other governments are looking at how well it rolls out in the States, and then from there, hopefully we'll see it overseas as well. But the general idea is you can use this spectrum, and there are a number of different types of antenna devices on it. You can have a small device, much like your little Wi-Fi router that's located maybe in a room like this or a small office, and the spectrum's being used there. You could put a larger antenna up on a cell phone tower, and your office could connect back to that larger antenna and then connect it onto one of the micro data centers. The use cases, so we've got one of the early use cases is augmenting 5G. So telco goes out, maybe there's a rock concert going on or something else, and they need additional bandwidth at that for their 5G network. CBRS can be used to augment that. Now, CBRS can also be used in an enterprise location. So maybe your company has got several buildings and they want to use CBRS to connect them all together. That's definitely another use case for that. So that would involve putting up antennas, putting up devices. The chipsets are available to use CBRS as well. And the use case that I'm talking about here is your IoT devices, your end user devices, your mobile cars, autonomous cars, using CBRS to connect back to a cell phone tower and then to a CBRS and antenna, that would then be connected into compute infrastructure located within one of those cell phone towers. So who's doing this? Who's involved? A bunch of different players involved. So we have, in the States, we have real estate investment trusts, REITs. So Crown Castle, American Tower, SBA. They're the companies that own the land and the antennas, and they typically rent them out to the telcos in the world. So AT&T and Verizon, historically, they've gone out and they've sold their antennas to these REITs. They're all publicly traded companies who in turn then rent it back. Federated Wireless, they're the ones that have been working with the government to get this spectrum available. So they're involved on the spectrum side. And then the compute power that goes inside of these locations. Packet is a bare metal cloud provider. And so what they've been doing is putting compute, so you've got x86, you've got ARM, you have GPU systems in these data centers, and they're available via API on demand. You make an API call, integrated in with Terraform, and then also software-defined networking to patch them in to the CBRS spectrum. So the end result is you can make an API call, get computers allocated at the edge locations that you wish, be billed by the hour for them, much like you're billed for a VM, but these resources would be bare metal resources at the edge location that you desire. And you run them for however long you need to, and then tear it down. So all of a sudden, you don't need to have a lot of skin in the game to get access to the edge infrastructure and the edge spectrum. Okay, so here is one of the first ones being plugged in and turned on. This is late last year in Boston, out at Foxborough Stadium where the Patriots play. So this was one of the first three that got turned on. So interesting use cases if you think about it, right? These are going to be right there at the football stadium. So they could get video streams from the football stadium, access control, security, controlling drones, maybe showing that are flying overhead at the football stadium. So interesting location. Other locations that got turned on last year, so we mentioned Foxborough, Chicago, Illinois, and then Las Vegas at the Miracle Mile Mall there. So that brings in some interesting use cases around retail and maybe entertainment. So we have 3 locations up, and they all have waivers from the US government, from the communications FCC, to turn those ones on. So what happens is the FCC goes and gives you a waiver to do it for a certain square mileage, that you can run them. Here is, I believe this is one of the Chicago ones. So the outside you can see there's the data center down there at the base of the tower, and then going up you can see all the antennas at the top. And then here's the internal of one of them with all of the packet bare metal machines plugged in. So very similar to, for those of you in the Openstack world, to an ironic bare metal cloud, right? Make an API call, gets access. So that's the hardware side of the world. Let's talk a little bit about the software side, which I think software is really what makes the world spin. We've got all of this infrastructure rolling out, and from what I've seen, the software still needs to catch up to really make things happen. Obviously, one of the big ones is Kubernetes on the CNCF front. So it's this clustering software. So how does Kubernetes run in an edge location like this? Do you want to spin up multiple clusters within each of these towers? How do you move your containers from cell tower to cell tower as your user base moves? Maybe your user is close to one of them, but then your users move, or let's say a bunch of users turn up somewhere else. Kubernetes or some type of control plane is going to have to be intelligent and know where the users are. And right now, Kubernetes is really focused in on deploying containers where the computing resources are. And we need to switch that scheduler and placement algorithms to instead turn on containers where the users are and where latency would be minimized as opposed to best use of the computing resources. So on the Openstack side, we've got Starling X, and Starling X just a couple of weeks ago has been given access. So there's an agreement between Packet and the Openstack Foundation, happy to announce, that has given Starling X access to these locations. For those of you who don't know, Starling X is an edge implementation for OpenStack. So it'll go through and deploy OpenStack across all the locations, but you still sort of need that control plane of where should the application run? Where should the VMs be running? Which one of the cell phone towers? And what are the applications running on top of it? We still need to find out what those applications are. Are they applications that are going to sit on top of Airship to control the self-driving cars, to control the drones? So it's a multiple layer. And then on the Linux Foundation side, they've got their own set of applications that they're running, or their own set of middleware that they're running with as well. So we got multiple companies going, multiple foundations in this effort. So let's talk about one application in specific. I just grabbed this because it's an open source project, and actually there was an email across the OpenStack user list a couple of months ago. Someone said, hey, I need a open source solution to do video conferencing. I don't want to use Zoom because there's only half an hour, a limited number of users. So I suggested Jitsi. Jitsi is an open source video conferencing solution. It's available for mobile devices. You can spin it up in a VM in a matter of minutes and it's up and going, and then you can connect in. So open source, easy to start, runs on a VM, mobile users. I see this as a great sort of trial edge application, and how might we take Jitsi and modify it to run on one of these edge locations? So one thing the Jitsi team has done is they've put intelligence in their application so that if there are multiple servers running, the end users will connect to a local Jitsi server, and then it'll do Jitsi server to Jitsi server, sort of a backbone connection between the two. And it's called their cascading solution, and that results in improved performance. Here we can see some numbers that they've gone through, implemented, tried it out, and seen how that works. Well, that works great if your users are static, if your users are always in the same place. But what do you do if your users are driving down the freeway and they are moving from one cell phone tower to the next cell phone tower? What does Jitsi need to do to track these users and figure out what location to put them on? And what do you do when you have hundreds and thousands of edge locations where Jitsi can go and instantiate copies of itself and then direct its users to? So this is where I see the edge software falling apart, and we haven't gone through and spent enough time thinking through. We need to improve the placement algorithms. We need to provide the applications, such as Jitsi, some sort of middleware layer that'll go through and do that on behalf of the application. Track the users, provide the direction of where the users are, and turn on multiple copies, turn on VMs of the application, turn on containers of the application on the application's behalf, and make that happen. So if there are people that are interested in this and you have applications or you have a project and you want access to the CBRS spectrum or some of these edge locations, Packet does have an edge access program. That's what we gave the Starling X team access to. So if you would like access to that infrastructure, come see me. Happy to get you in touch, and we can see about getting you access to some of that infrastructure. Thank you. Any questions I can answer? No? If not, you're welcome to come see me and enjoy the rest of the conference. Thanks again.